This is Mrs. O'Neill for Chapter 12, Section 3, Limiting Reagent and Percent Yield. In this section, you're going to be able to explain how the amount of a product in a reaction is affected by an insufficient quantity of any of the reactants. We're going to be able to calculate percent yields and what that measures for a reaction. You should have watched that intro information on limiting reactants and percent yield. Here are my notes. So guys, a limiting reactant is the same as a limiting reagent. Reactant and reagents are the same word for the same thing, reactants. So he talked about making cookies, and he said, well, if the recipe calls for 2 eggs, but you only have 1, it's going to limit how many cookies you can make. It's going to limit the reaction from occurring. But you can still make cookies, right? All you got to do is cut all of those ingredients in half. So this sometimes works for reactions and sometimes it doesn't, but it's very, very similar to what he's talking about as far as what limits the reaction from continuing to happen. He talked about the coefficients equaling the amount, and that's why when we talked about mole ratio, that mole ratio was going to help us understand how much of what we can make comes from what we have. So he talked about that hydrogen combustion reaction. So he has a starting point here. He gave us a whole bunch of reactants, a whole bunch of, excuse me, hydrogen molecules and oxygen molecules. And he said, well, this is how many waters we can make from how many reactants we have. So how much products we can make from the amount of reactants we have. And from the reactants that we have, though, we're going to have some things left over. So we have oxygen left over, which means we've used up all of the hydrogen, which means that hydrogen is our limiting reactant. It's going to limit the reaction from occurring. Then he came up with another example, our combustion of methane. Again, in the lab, we use a Bunsen burner. That's methane gas being burned with oxygen in the air to give us that CO2 and water. So again, here's our starting point. This is how much methane we have, and this is how many oxygen molecules we have. So how many products can we be making? Well, we can make 1 carbon dioxide and 2 waters, but if you count up all the atoms like he did, again, what's going to be left over? Well, methane was the limiting reactant because we only had 1 carbon here, even though we have plenty of oxygen. We have oxygen in excess. So again, he was trying to get you to understand that for most reactions, we have what's called a limiting reactant, and we have a reactant that's going to be in excess. We have more than enough of it. So again, but he talked about how atoms are so tiny, so we have to always refer back to our friend, the mole. And again, it's going to go back to that mole ratio. So he did an example problem. So he talked about how we started out with 10 grams of each methane and 10 grams of oxygen, and he converted those again to moles. Moles is our friend. From moles, we're going to compare moles. So if you notice, guys, we went from moles of methane to moles of carbon dioxide. He chose one of the products to go. You could have went to also water, doing the same thing. Most of the time in your problems, guys, they're going to tell you what product they're going to want the answer for. So from here then, now that we're at moles of CO2, we can go back to grams of CO2 and how much product would we actually make. And looking at these products or comparing the products, we notice that, yep, oxygen is our limiting reactant in this case because it made the least amount of carbon dioxide. So as a chemist, guys, you always want to make your most expensive chemical be that limiting reactant, right? You want to use the least amount of that as possible and make sure that you're not going to waste any money. Oops, sorry guys. And then he talked about predicting yield. And for our purposes in our notes, we're going to be referring to predicted yields as theoretical yield. And that theoretical yield is basically if the reaction is perfect and goes exactly the way you want it and all the conditions are perfect, you're going to get the amount that you truly want. You're going to get that stoichiometry amount that you want. However, the actual yield is usually less than predicted yield. The actual yield is the amount of product that you actually made in lab. So it's the comparison of the two. So again, for percent yield, you're going to want that 100%, right? You want 100% of that product that you've made. So again, there's this formula that he used. So we're going to take the actual divided by the predicted times 100 to give us that value. And he says it's usually never 100%, right? It's either going to be less or even sometimes more, but in this case, it's 90%. So this is a good reaction. If you have 90% yield and you were supposed to, again, you made 6.19 grams and you were supposed to make 6.88 grams according to stoichiometry, 90% yield is actually pretty good. That means that reaction went pretty well. So to your notes packet, if a carpenter had 2 tabletops and 7 table legs, he would have difficulty building more than one functional 4-legged table. The first table would require 4 of the legs, leaving just 3 legs for the second table. In this case, the number of table legs is the limiting factor in the construction of a 4-legged tables. A similar concept applies in chemistry. The amount of product made in a chemical reaction may be limited by the amount of one or more of the reactants. So guys, again, pause the video, read as you write, fill in those blanks, and then play to hear my words. So just as a reminder, limiting reagent is the same as a limiting reactant. It's going to determine, this particular reactant is going to determine how much product can actually be formed. It's the stuff that gets used up first. So obviously when that reactant is now a product, right, is used to make that product and there's no more left over, that means no more product can be made or can be formed. So of course, then that other reactant, if there is a second one, is going to be in excess. We have some left over, all right? So there's more than what was needed in that reaction. So examples in your notes, there's a little chart again. You're going to draw those particles. My strong suggestion is kind of listen to everything I'm going to say. And at the end, you're going to see my last slide to pause and then draw things in. But first, let's look at this reaction on the microscopic level. So we're going to look at these nitrogens, hydrogens to form ammonia. So this is the true chemical equation. However, how about if we have different experimental conditions? So how much product can we make if this is going to be our starting point, not the true reaction, but an experimental condition? So why don't you just pause for a second, though, and think about how many NH3 molecules can we make when we have 2 nitrogen molecules and 3 hydrogen molecules. Hopefully you paused and you came up with the fact that you can make 2 molecules of NH3. But the problem is there anything left over? Do we have anything left over, or did we use everything up? So again, pause and give that some thought. You probably already know this answer. So if you came up with 2 molecules of ammonia, you probably said in your head, well, that means there's still 1 molecule of nitrogen left over. So what does that mean? Well, which reactant then is going to limit the reaction from making more product? Our hydrogen. We don't have any more hydrogen molecules. We don't have any more hydrogen in our pot, let's say, to combine with nitrogen in order to form the ammonia. So that particular reactant, the hydrogen, is going to limit the reaction from occurring. That's going to be our limiting reactant. So then what's in excess? Well, nitrogen. We have plenty of nitrogen left over. And if we have that nitrogen left over, it's in excess. So again, think about this, guys. If we are if we are a company to make ammonia, we want to know the exact amounts of nitrogen or hydrogen that we need to make so much ammonia. Or, ladies and gentlemen, we don't mind having an excess of the cheap reactant, but we definitely want to have our expensive reactant limiting so that we don't waste any more money. So again, at this point, pause the video, draw and label your reaction here again, because these are the experimental conditions and not the actual reaction that occurs. All right, so hopefully you did that. Again, going back to the chemical equation, this is our normal chemical equation, and we're going to now focus on that mole ratio. And that mole ratio is going to help us decide mathematically what reactant is going to be our limiting reactant. And of course, then the other guy is the one in excess. All right, guys, see you later.